I want to talk about the stars. Uh, well, first, actually, I want to talk about cans. No, we'll talk about the stars, and then we'll talk about cans. All right, let's go to the 16th century. Let's go to Denmark. Humanity has been looking up the sky for thousands of years, and they're starting to figure some things out. One of the things they're figuring out is that they should really just collect some data. They should look up, take notes, and figure out what's going on up there. And so there's a tremendous interest in the movement of celestial bodies. And it's just becoming possible to observe such things. We don't quite have true telescopes, but we're beginning to build the technology that allows us to have observatories and eventually gather all this data. Now, there's a young man who is uniquely obsessed with this topic. He's a very unique and unusual man. And he goes around with something of a quirk. You see, he is missing his nose. He lost it in a sword duel with his cousin when they were students. And so he goes around with a brass prosthesis. You might think that such a person might find it hard to make his way in society, but he actually gets the attention of the king and is able to compel a tremendous amount of resources to be dedicated to, of all things, science, to stare up into the skies and to study celestial bodies. This man's name, pronounced in my accent, is Tycho Brahe. In Danish, I think it's a little bit different. Now, he spends decades of his life staring up at the stars, and gathering all of this fine-grained data around their movements at a level that had never been previously collected. And it begins to tease out a story that takes much of the rest of his life to begin to pull apart. Now, just to be able to do such a thing, he has to compel the king to give him an entire castle with gardens and buildings and entertainment just to be able to house this operation. This goes on for a fairly long amount of time, and he gathers more data than really anyone had ever gathered before in this respect. But eventually, like a lot of good deals, it comes to an end, and so he has to go to Prague. Now, in Prague, he is able to still secure patronage and continue his research for the rest of his life, but he has the good fortune of hiring a young employee and who is also interested in these same topics, who he eventually develops something of an acrimonious relationship with. The young man's name is Johannes Kepler. Kepler is also interested in the movement of celestial bodies, and so working for Brahe for many years, he begins to see what exactly is all this data. But they end up fighting over the data and not being able to agree with how the data should be used. There's one really big advantage, though, that Kepler has over Brahe in this disagreement, and that is he is younger. Eventually, Brahe dies, and Kepler inherits his data. From that data, he is able to take those final steps, going from this unprecedented data asset that characterizes the movement of celestial bodies into being able to formalize this into incredible new insights that derive very compact mathematical formulas of the movements of the planets. Chiefly, he figures out that Mars moves in elliptical orbits and then is able to project out centuries into the future incredibly accurate projections of where the planets will be. Now, this is a very famous story in science, but it's a sort of rhyming beat in science. We often go down this path where we have to collect up all of this data, where we have to observe the world as it is. We have to be very empirical, and we may not know everything about how all the pieces fit together, but as we characterize them and we accumulate this additional knowledge, we're able to then later create something that is more abstract, more compressed, and that delivers deeper insights and allows us to build higher and higher levels of science on top of that. And so this beat is our topic today. Our central point of consideration will be a technology called a CAN. And we will dive in with a little bit of special guest help as well. And we're going to go a little bit deeper than we usually go here. This episode is very much open to beginners, but we are going to talk math. We are going to talk about the low-level details of GPU optimization. And we're going to talk about where science comes from. I'm Jet, and this is Iterative Refinement. So to begin this deep dive in this episode, I need to introduce our true central character of the episode. And to do that, I'm going to require a little bit of help. So our central character today, I'm going to call the can. But formally, its name is the Kolmogorov-Arnold Network, invented by Ziming Liu. And we're going to talk a lot about how it works, how it gets applied, and some of the unique things that people are just now figuring out how to do with it. But to begin to dive further, I'm going to have to bring in more of an expert, our resident mathematician, Robert Ronan, to explain more about the history of the mathematics behind cans and how they work. Take it away, Robert.
Before we get into the can-specific math, let's go back a little bit further. In 1900, David Hilbert compiled a list of 23 unsolved mathematical problems he considered to be fundamental open questions in mathematics. The 13th problem on that list asked whether the root of a general 7th-degree equation could be expressed as a finite composition of continuous or algebraic functions of just two variables. Solving 7th-degree polynomials initially presents as a function of 7 variables, since if x is the root of x to the 7th plus ax to the 6th plus bx to the 5th, and so on, plus fx plus g equals 0, then solving for x is a function of a, b, c, d, e, f, and g. However, it was known at the time that these equations could be rewritten as x to the 7th plus px cubed plus qx squared plus rx plus 1 equals 0, meaning the root x could be thought of as a function of 3 variables, p, q, and r. Hilbert had proposed that it was not possible to rewrite this as a composition of continuous or algebraic functions of fewer than 3 variables. In the 1950s, Kolmogorov and Arnold proved what is today called the Kolmogorov-Arnold representation theorem. The theorem states every continuous function on the unit n cube can be written as a finite composition of sums and continuous univariate functions. Specifically, it says if f is a continuous function on n variables from the n-dimensional unit interval to R, then there exist continuous univariate functions phi q and phi qp, such that f of x1 through xn can be rewritten as the sum from q equals 0 to 2n of phi q applied to the sum from p equals 1 to n of phi qp of xp. This addresses the continuous portion of Hilbert's 13th problem, as it implies that every continuous multivariate function can be reconstructed as a composition of functions of 2 or fewer variables, since addition is a binary operation. But what this means more broadly is that there is only one true multivariate continuous function on R, and that's addition. Every other multivariate function, division, power, multiplication, can all be written as composition of univariate functions and summations. While some attempts have been made to leverage this theorem for machine learning, it has been widely regarded as true but irrelevant, since the univariate functions it produces are not and often cannot be made to be smooth and well-behaved. Instead, it may produce functions like the Weierstrass function, which is continuous everywhere but differential nowhere. However, Liu et al. Recontextualized this and used the representation theorem in their 2024 paper, Kolmogorov-Arnold Networks. They propose learning the univariate functions with backpropagation rather than computing them analytically, and further propose restructuring the composition of functions to be of arbitrary width and depth. Before we get into the can-specific math, let's discuss a little bit about B-splines. B-splines are piecewise polynomial functions designed to take non-zero values over only a small number of intervals. These are the core components of cans, as we'll discuss next. Specifically, B-splines are curves, defined by the degree of polynomials that comprise them, a knot vector, which defines a set of breakpoints, and a set of control points. The knot vector is a sequence of non-decreasing numbers, which determines essentially how much time the curve spends in each segment. The more knot points you have, the more control points you have, and the finer you can control the individual sections of the curve, and the more expressive you can make the B-spline. The control points manipulate the shape of the curve, essentially pulling the curve towards them, and the degree here is the degree of the curve segments. Degree 1 would mean lines connecting sequential points. Degree 2 would mean quadratic polynomials. Degree 3 would mean cubic polynomials, which is the standard choice and is used by the CAN paper. What makes B-spline special is that each control point has a corresponding basis function that essentially scales the weight for the control point as you move across the intervals. The spline itself is the weighted sum of the control points and their respective basis functions, but evaluated at different points along the interval. Since the basis functions are defined to be 0 outside of all but a few intervals, this gives you local control over the shape of the spline. It means that manipulating one control point affects only the shape of the spline locally rather than globally. Compare this to a polynomial fitting, where moving one point slightly leads to drastically different behavior across distant portions of the function. Now let's get to the actual CAN architecture. For some grounding, let's recall how a standard multi-layer perceptron, or MLP, works. These are also called vanilla neural networks or dense neural networks. In an MLP, there are layers of neurons connected to the layers before and after them. Each neuron here computes a weighted sum of its input and applies a nonlinear activation function. The learnable parameters here are the weights, which are linear and comprise the edges. The nonlinearities in an MLP are fixed at the start of training, since moving them around during training causes significant chaos for the network. In a CAN, each edge carries a nonlinear univariate function rather than a scalar weight matrix. The univariate function is parameterized as a B-spline, like we discussed before, and the neuron simply sums the output values of the connected edges. In a CAN here, the nonlinearities are the learnable features. In a CAN, the B-spline has a fixed basis function, but the control points are scalars and are learnable. Since the basis functions that make up the B-spline are local, CANs provide the ability to add more knot points, or grids as they're referred to in the paper, to increase the expressivity of the nonlinear functions. This can be done during training because the structure of B-splines allows for local changes. CANs are probably best thought of as inspired by the Kolmogorov-Arnold representation theorem, since they take it from what would be a fixed layer, a fixed width 2-layer composition to an arbitrarily wide, arbitrarily deep network, and they add residual connections and a handful of other changes to make it smoother and more stable. This is not to say that CANs and MLPs have fundamentally different expressibility properties. Both of them are capable of representing arbitrary continuous functions. It's merely a question of the structure of the network. In the same way, both dense MLPs and convolutional networks can be used to process images, or dense networks and transformers can both be used to process language. It's merely a question of which structure does the better job.
I hope that was helpful and informative. I find this topic incredibly rich, and I think even if you didn't follow every single beat of the math there, I think you'll be able to follow the rest of the arc of where this work leads to within its application within AI research. Now, CANs are the result of a larger research team, but are substantially led by a researcher named Ziming Liu. Now, he's a very opinionated researcher, and he has a very grand vision. It is his metaphor of Brahe and Kepler that we begin this episode with. And so I'm going to introduce some of his language for how he frames his own research, and we're going to consider it as our mental model for the episode. These are not necessarily the terms that everyone uses, but we'll go with it. So one of the key points that Ziming often calls out in his blog posts and other appearances is the idea that scientific problems are regression. and that ultimately the history of scientific theory is the search for a symbolic regression, a more abstract representation of durably true laws. But sometimes we need to begin with something that looks like what he would call empirical regression, which is more of a taking the data for what it is and deriving these sort of descriptive functions which in some way characterize the behavior quantitatively, but do not necessarily derive symbolic new insights that have the ability to be composed in different ways. And so his classic description of this really kind of points you towards this idea of what he would call structural regression, is that if, say, a symbol like c, the speed of light, is really something that is durably true, and that like an empirical regression that, in general, animals have roughly this number of heartbeats if they're vertebrates within this size range, that there are some things that have patterns of a different sort that we're going to call structure. Now, structure means things like modularity, hierarchy, uh, compositionality, reusability, sometimes sparsity. Structure shows up all around the universe, all throughout natural life, and that insights at the structural level, even if you're not able to proceed all the way to a fully symbolic level, can be incredibly powerful and are really a different paradigm that sit in between the sort of world of the empirical regression and the symbolic regression. This is the intuition for some of this work on brain-inspired modular training, BIMT, but we're going to focus on some of the later work on CANs. All right, so to understand CANs, I'm going to revisit some of the things Robert said, but I want to really kind of hammer home how they sit within our landscape of the modern AI research tool chain, of the methodology we bring to bear. So the most common tools we bring to bear within AI research these days are multi-layer perceptrons, typically transformers, typically using attention, and activations like ReLU, rectified linear units. Originally, they were all dense. These days, they can be sparsified. It might be mixtures of experts, but this is our sort of core methodology. This is straight down the middle, whether we're talking about vision, language, speech, code, you name it. Now, CANs are somewhat different, obviously. So CANs don't have that same sort of simplicity at the level of the node. In fact, they use these really expressive, rich atoms. And so if the node of a dense MLP, or ReLU, is actually really, really simple, you can just graph it like that. The expressiveness of the CAN in the B-spline or alternative function there, it it needs to earn itself. And so why do we have complicated atoms in this approach that CANs put forward? Well, this gets into a framing that sometimes gets discussed as reductionism versus holism. And so in the CAN space, when we have these sort of very rich mathematical functions that allow us to say something about a particular structure, the hope is that this is mapping to something that is informative and that is a very dense representation of a meaningful behavior that could possibly be understood and composed and used modularly. The alternative is how we use LLMs today, which is holism. Now, holism in this sense means we're ultimately doing this sort of connectionist paradigm, which means there is this statistical association between all of these things, but it's really the whole network that knows things. And so it's different activation paths for different queries at different tokens going through an LLM. They are all unique bits of knowledge, but you really kind of need the whole LLM to really understand its behavior. That means that things like interpretability and compositionality aren't a given within LLMs and are really not necessarily always achievable. And so there's different reasons why that's going to help you or hurt you depending on your use case. And so you can think of this in terms of inductive biases. And so there are some things we want to know which correspond to the shape of a modern LLM. They are within knowledge that has at some point been written in a book or on the internet, that may be distantly connected to other knowledge that is also written in a book or on the internet, that share certain tokens in common. There are sentences that refer back to each other. And so our inductive bias should say that using an LLM to answer such a problem is going to be really powerful. But when, for example, we're trying to model physics, it can be shown that uh, LLMs are actually quite poor at that task. And so you can read some of the literature on CANs and some of Ziming Liu's blog posts that talk about things like showing how a CAN can understand meaningful physical equations such as Hooke's law. Okay, so I'm going to continue our orientation. I want us to think about where we are at this point within the cycle of the progress of AI research in this field. And so there have been incredible results that have come out of pure scale. Early NLP, as I remember practicing it earlier in my career, was really focused on these like specific data sets. And so, for example, when I was working on meeting scheduling via email in a sort of early conversational agent, one of the things we worked with was assessing the value of a very specific business data set. For example, the Enron emails. Could we derive just from this open data set of people scheduling meetings via email? Could we learn the concept of scheduling meetings via email from that? It's a very narrow slice view of things. What the history of LLMs and this era of Gen AI has shown us is that there are emergent properties in these models where we shouldn't want to just learn how to schedule emails, but we should want to read every single thing that has ever been written in any context. And from that, we get what are called emergent properties. Those emergent properties are things which may or may not have been designed in, but they exist within the structure of the knowledge that was encoded in the training base, and thus the immense flexibility of attention-based techniques in LLMs allows us to have picked up those skills, which were really just encoded in a very unopinionated way and require that sort of scale. Now, one of the things about scale being the big unlock to LLMs is that it can get a lot of people who are, for example, not AI researchers or AI researchers who only came up during the era of LLMs. It can give them a sort of miscalibration for exactly the shape of intelligence. And so one of the really desirable properties of intelligence that many researchers would point to is compressibility, the ability to say that this bit of knowledge can fit within a much smaller package, and so that we can understand things about it and compose it and reuse it in different ways. A really simple example would be something like defining the mass of a snowflake, which is incredibly tiny. The movements of stellar bodies, that's another really compressible bit of knowledge. Um, and more recently, as people have worked within a range of different problem spaces, you see tremendous excitement for things like SVGs, which were not a particularly popular media format, but are actually a tremendous area of innovation within coding AI research because they are highly compressed representations of visual media in contrast to something that is substantially more dense and inefficient, such as a pixel-based method in a stable diffusion. So this is not an either-or with respect to humanity's knowledge. Humanity has explored techniques that have both of these properties, but we want to spend some time understanding what what are the shapes of problems that really are amenable to the search for compression, and what do we get when we find the ability to find a more compressed technique. One of the metaphors that Ziming Liu likes to lean on is this idea of kind of mapping to different sorts of sciences. And so, at our level of LLM-shaped problems, these things which are really very weakly compressible, that they don't have strong rules to them, that we really just kind of observe via these sort of empirical regularities, these rules of thumb that we have experimentally validated and done sound science on, but have not achieved a higher level of abstraction. Let's call these biology-shaped problems. Now, the good old-fashioned AI of a generation or two ago, what people really conceived of, back at Dartmouth at the absolute birth of the artificial intelligence field roughly 70 years ago, they really thought in physics-like terms, or if you prefer, math-like terms, which is highly abstracted, purely symbolic forms of intelligence. Work like this is important. It's part of how we got here, but it's not actually the stuff we're using in a lot of these circumstances. Typically, the world sits somewhere in between. There are what are called neurosymbolic systems, where we made up systems which have some properties of this connectionist statistical association LLM sort of world, up with things which have a higher level of abstraction, such as traditional symbolic techniques. And there are things that sit really at that boundary there. And we can call this, Ziming Liu likes to call this maybe a chemistry-shaped problem, and points to things like EQL as a sort of neurosymbolic space. But ultimately, cans are this next level of trying to get to something that is structure. Now, we we don't reason a lot about our structure inside our modeling techniques at the sort of fundamental methods that have enabled the LLM era. And this may not be obvious to people who are consuming them, but for people who are developers working with an LLM basis, you're probably familiar with all of these ways in which we impose upon an extrinsic structure into our usage of LLMs. So those extrinsic structures tend to be things like the original approaches to inducing chain of thought. Agent frameworks are probably the absolute largest space where we do all of this human authored code to develop all of these behaviors which we want LLM powered coding agents to take. And as well as all sorts of reasoning scaffolding. These are things like deep research. And so these are ways in which we can impose structure, but it's not learn structure, and it's not necessarily new fundamental insights into the science. So the so let's get us deeper into, like, how does cans fit in this space? Well, originally people really kind of looked at cans and saw, oh, that's kind of built for doing, just reverse engineering physics. And so people tried on physics shaped problems where there actually was a sort of dense and meaningful equation that could be learned. And that's some of the absolute earliest results. And as you can hear from Robert's mathematical introduction to cans, it's sort of obvious why that mathematical intuition would lead to a way of learning new extant examples from math and physics. But as people saw the benefit of the can technique, they really got very excited about lots of different things you can do with cans. And so some of those things are sort of pragmatic adaptations that really kind of get beyond the work of Kolmogorov and Arnold. And these are things like adding multiplication. Some of the things I find really most interesting are things which compile into cans. A lot of my work that I'm going to discuss in the following section is about compiling to and from cans. Um, this is a really powerful technique. This is one of the signs that we've got abstraction, though, is that we can pass through multiple representations, that we have a compression. I'm going to dive a little bit deeper into what this means in practice. Another sign of this is people being able to do things like map between cans and tree structures and so forth. And so there's been a lot of progress on the theory and the practice of these things. One of the things that at first maybe didn't create as much excitement around cans was the signs that in the sort of apples to apples case, cans look to be extremely difficult to deploy, that they were substantially less parameter efficient, and that this might create a lot of problems with making the real world useful. My work and the work of others gets into this topic. There is possibility here that we can make cans efficient because they have that abstraction. All right, so I want to talk about two specific examples. This is work that I've led in the second case with a collaborator. And so these are attempts to take a look at cans and understand what else they can do, and really see if they can be brought further to application contexts, which we already know are meaningful. The first bit of this work is a bit of vision work that is focused on on-device deployments. And so to tell you a little bit about our data set and our presumed deployment architecture, I'm thinking of things like drones, like robots, like industrial robotics, like security cameras, so on and so forth, where you have a camera in a real-world environment. We care about how much intelligence we can fit in the package. We're assuming that inference is purely local. Our energy usage matters. Our latency matters. Standard edge deployment stuff in a vision context. We're going to compare the existing techniques of different sorts of MLP-based models on well-known data sets. In this case, we worked with Pascal VOC, which is an object recognition data set. And then we're going to try and figure out how to solve this problem of cans. Now, when you get down to a constrained device, you can find that computers aren't free. They are not infinite in size. You have to really, really think about what are the constraints. Most commonly within a neural network being deployed on a device at this point, our key concerns are things like the memory bandwidth wall. And so this is about the speed of getting memory, about getting data from memory as being one of our key constraints there. This has to do with also how much information we're storing at which level within the memory hierarchy, and thus which operations need to occur. This has impacts on the amount of intelligence that can fit within a given envelope, the latency, and the energy usage. And so solution explored within the technique I developed, which is called ShareCAN. So in ShareCANs, which stands for Spectral Hardware-Aware Representation of Kolmogorov-Arnold Networks, we're in this particular paradigm. And so what we want to presume is that we don't want to use the expressive power of CANs to develop a rich understanding of the vision concepts. However, if we do that naively, we will find that we need quite a bit more parameter space than an equivalent MLP, often meaning that we're not sitting within the same deployment envelope. We can be off really by about 2 orders of magnitude, roughly 140 times in my experiments, which sounds like it's going to be really, really crippling. If you attempt to prune this in particular ways, you may or may not get down to, as an attempt for sparsification, this sort of crude form of compressibility we often use in connectionist techniques, like dense MLPs. When we try to get to that sort of compressibility via sparsification, performance collapsed here. Now, there's an alternative approach here, is because remember the CAN is a learning system that has believed a meaningful structure to it, and so that structure should be compressible. And it turns out it is. And so the actual spline shape itself can be tremendously compressed. The ways in which you do that is you break that into 3 units. These are 3 scalars. This is a gain, a shape vector, and a bias. And with that, you can reconstruct the shape of the original spline. Um, these values can be stored within what's called a codebook, which is just a way of memoizing this information. And you can accumulate this information in a scale which is defined per the resolution that you have available within your envelope. And so in this case, this is roughly 65,000 entries per layer. And this gives you an extraordinarily high level of reconstruction at a massive savings within your footprint size. And so you retain 98.5% of your performance of something that was previously undeployably large. Now, getting down to those scalar values means you do have to reconstruct them at runtime. And so getting them back out means that you need to define this sort of special operation lookup to be able to do this. This uses techniques within executorch. The runtime built here, we call this LUTHM, which is for lookup table hardware aware mapping, which is this sort of technique to use lookup tables to reconstruct out the space, the shape of the spline from our values based on really efficient scans based on the values within these sort of quantized ranges. And so we've quantized down our splines to be able to map them to these sort of finite 3 scalar values of our gain, shape, and bias, and then reconstructed them by a LUTHM. It's interesting to note that this is a technique that you may not have personally deployed before, but you've probably already experienced it, particularly if you were alive in the 80s and listened to a lot of synthesizer music, that the Casio keyboard and really all synthesizers of that era use the exact same techniques of this sort of quantized compression of waveform shapes. This sort of lookup form. That's how you get the ability for a tiny amount of memory at the time to be able to represent everything from a flute to a violin to a trumpet and so forth. And so this technique has the same sort of applicability within the case of being able to give us a new way to deploy the intrinsic compressibility of the CAN to get us within our deployment envelope. Now, we're not exactly at a win-to-win yet. So win on a one-to-one basis, because all we've gotten to is really the ability to deploy. It's about an order of magnitude more efficient than a dense CAN at this point, with minimal accuracy loss. But we're really only at the same level of performance. And in fact, at a head-to-head basis, where the dense MLP of our sort of ResNet comparison point is actually a bit smaller. The real benefit here is that compressibility doesn't have to just be used once. The value of that codebook can be recomposed. You can just add more instruments to the keyboard. And so you can accumulate orders of magnitude more experts. And so you can specialize across different tasks, accumulating expert heads within approximately the same size codebook. And so you get this sublinear scaling of addition of experts. We call this technique mesh cans for mixture of expert share counts. So I think this is an interesting approach. Vision is not really my home territory, but I think the idea that cans hold up to this amount of engineering optimization for specific devices here. In this case, we're really thinking a lot about the size of particular. This is the Ampere architecture within NVIDIA's hardware, and thinking about exactly the memory footprint we have available on deployable devices. The abstraction really, really pays off. And so this may seem like a lot of transformation to kind of get back to where we were the first time around, but the efficiencies are actually quite large. And so we're able to have roughly 50 times as many experts, but within the same deployment footprint. But we also have a much, much cheaper inference operation because we're no longer doing the same sort of operation to be able to do a bunch of floating point calculations to actually get to our prediction as we would be doing in the dense MLP. We're doing a ton of our work with substantially more efficient lookup tables, and so we're looking at energy benefits by sitting higher in the memory cache and then higher in the memory hierarchy on the order of 2 to 3 orders of magnitude. Okay, so that's one technique. You can read that paper. It's got a preprint on arXiv. It'll probably be at a conference at some point. I want to bring you into another example, which I think brings in a little bit more of these techniques and might feel a little bit closer to more of your home territory, whatever that may be. And so in this case, I'm going to talk about a line of work we call Brill Agents. This paper doesn't have a preprint up. It will be at a conference at some point in the future. At the moment, I want to just talk about a specific method that we observed within this work. But to do that, I need to define our task space. And so our task space is we're building agents. Isn't everyone building agents? Every day you open up LinkedIn or Twitter and you see someone else has launched a new type of agent that does a new sort of thing. Well, a big part of this work is to revisit what did we originally intend by agents from the decades-old literature of how we define them. What are the properties we lost in this sort of reduction of our working definition of agents, and our premature optimization on the properties of LLMs and how they can allow for the creation of an agent-like concept that lacks a number of properties I think of as deeply important to what is really meant by an agent within the academic computer science literature. The part that we're going to focus on here is learning. Now, it may not be obvious to you if you run something like an OpenClaw or something like that, but your agent isn't really learning in the way that we would usually conceive of it. It's accumulating fixed context in static data, but not actually changing any of its knowledge. It does not update its weights. The model is really deeply unchanged at the intelligence layer. In fact, we just have sort of different tokens being injected in through the accumulation of markdown files. And so people who perceive a Claude code session or an OpenClaw instance as having learned a lot about their project or about themselves are seeing a sort of limited form of in-context learning entirely predicated on the persistence of data at rest. This isn't really the only way to do it. And so one of our challenges here in learning in something that is deployed in real time is that time matters. And so we as humans are able to think at multiple speeds. Daniel Kahneman is a famous researcher who's popularized this idea of thinking fast and thinking slow, what are called system 1 and system 2. We can call these things like reflexes versus reasoning. And so you can do both things like jump back and not get hit by the double-decker bus as it comes towards you because you were crossing the street the wrong way. But you can also then sit on the on the sidewalk and consider what is the likely fluctuation of the exchange rate between pounds and dollars, given the geopolitical context you find yourself in. You have a system one and a system two. You're able to jump back from the bus. You're also able to reason about macroeconomic policies. And so, transform to an agent, the standard LLM, with its fixed knowledge, its long inference times that are not fast enough to jump back from the bus, those can be used as a reasoning layer. They give us a system too, but the real innovation that Brill Agents work is in the development of a system one. Now, system one can be done a lot of ways. We could actually just build reflexes, really, really crude ones. And this is how you usually start at an academic level when you're learning how to build toy robots, oftentimes in just simulations. You'll build what are called reflex agents that have just hard-coded rules that you've built. But that's not machine learning. Machine learning means that we're learning from the data. And so if we want to use the system two reasoning model in an environment as a sort of data forge to be able to learn new knowledge from, system one must online self-distill that knowledge. It must be able to take the things that are happening when the agent interacts with any arbitrary context and turn that into new knowledge. In the case of Brill Agents, we took an approach that's heavily inspired by many of the systems properties of the Beam ecosystem. This is more commonly known by the programming language Erlang. This is a technology that was originally developed for the purpose of building highly resilient systems, primarily in a telecom context. It powers a lot of the systems that you've used to connect with throughout your entire life, at least across telecommunications. Also in things you may use every day, like WhatsApp, like Discord. Really, really powerful stuff. These days, a lot of people talk about this ecosystem really in terms of Elixir, which is an incredibly powerful language for modernizing a lot of these powers. In this case, we built Brill Agents in Elixir, and what Brill Agents do to construct a system one is that they learn a FastKAN. Now, a FastKAN replaces the B-splines with radial basis functions to be able to very, very quickly learn a CAN. Now, if we can very, very quickly learn a CAN, that means that every time system two has to take over and take an action, we can generalize from that. We can learn a CAN, and periodically we can compile that CAN into a representation. That representation can be turned into native Elixir code. That Elixir code can fill up a library of system one type knowledge, and we can use the unique property of the Beam ecosystem to hot code reload. That is, literally give the agent new knowledge about reflexes it should have to be able to respond to the same sort of latency. It has a huge, huge impact on the latency with which that agent can respond. It's also intrinsically as general as the system two. If system one does not know how to respond in the same fashion that system two would do so, it falls through. And so it's just as general and unopinionated, and thus as broadly useful as a system two general purpose LLM type agent, but it has the ability to learn how to be fast and to work within the real world, which is really important when we think about all of the broad applications of deploying agents around the world. Most agents are not capable of functioning in real time. They cannot make very rapid decisions. And so they are really quite poorly suited to working in use cases that involve, say, the physical world, that involve fixed time bounds. And so you don't see people running really slow LLMs to do things like financial trading. But it also means that you can't really power a robot's brain as it navigates the real world to deliver a burrito to your apartment with that same sort of no reflex, only slow reasoning type of mode. And so um, I think this was a really interesting discovery that this would work as well as it does. Um, I think it's a great sign of the ability for CANs to use their ability to help you understand the structure of mapping between inputs and outputs in some fashion, in a very general fashion, and achieve something that is incredibly compressible. The total S1 memory space is tiny in comparison, and its energy usage and its latency are so much better than the big, slow LLM that backed it, that initialized its knowledge space. And so it gives you the ability to do these specializations. Now, for me, I think it's obvious from my two examples here that I'm deeply concerned with how do we build the tools that allow us to take those next steps from where we stand right now. Now, if we think about what is the progress that was made in going from Brahe to Kepler. We went from data to a theory of that data. It's also worth noting that there was a lot of substrate work here. A lot of tools were built. Entire observatories were built. You really have to build up a lot of enabling technologies to get there. My research ideas often really come from more of an engineering background. That is really more of where I was primarily trained, and I do research as a secondary activity. And so when I think about what holds us back from using the best ideas we have in computer science, it often comes down to we haven't actually made the smart thing easy enough. And so this opportunity of so much connectionist intelligence is structurally inefficient, is unexplainable, is a really huge opportunity. And the methods which change that formulation, that allow us to see this situation differently, they open the door to a different sort of future where we can take advantage of that opportunity and build new shapes of technologies. And so I think that for all of the advances of the current wave of LLM powered technologies, all of this extrinsic structure is missing the opportunity to learn structure, to put that inside the ML loop. And I think that is the next big advance. And I think that those sort of structuralist techniques that find a way to abstract what they are learning allow us to get to a world that has different properties. And so I keep emphasizing things like how much energy does something use? How much memory does it require? What's its latency like? These may seem like they're, I don't know, prosaic or logistical, but they actually have a huge impact in your sovereignty. And I mean that's, big S sovereignty, but also little s sovereignty. And so what I mean there is that when you call a chat GPT, a Gemini, um, a Claude, it may be your account, but it is not your model. It is not deployable on hardware that you own. In most cases, it's not deployable on hardware you would have the funding to use directly. These are fantastically large, sophisticated systems that you do not have full control over. That also has like these weird implications where people expect that software is supervised by humans. But we're now developing software that is not easily supervised by humans. As you sort of reason through what is an LLM, what does the connectionist paradigm give us as a structure of intelligence, if it lacks this inherent abstraction property, we may never get really meaningfully better at being able to do explainability and supervision intrinsic to LLM techniques. We are stuck with things like guardrails and agent frameworks. To me, this feels like a clear limitation that the science will find a way past, but it will come probably through a paradigm change towards something that gives us a different sort of insight. And so I think that's part of some of the excitement of many people who, when they first came across cans, saw that these techniques were so good at deriving structures which could be interpretable that you could literally visualize spline shapes and derive meaningful knowledge from them. Another thing that really comes up is that we're starting to really let AI out of the lab. And I don't just mean things like, having AI do customer service or write your emails or, create your thirst trap pictures for your Tinder account. I mean things like actually interact with agency in the real world. And so this is things like continual learning, like world models, like robotics, where we want to deploy intelligence that is operating indefinitely, that is operating in high fidelity environments, including the absolute real world as perceived by sensors such as cameras. And we want them to do things that are possibly consequential, like go out on the street and, maybe run into traffic, maybe fall out of the sky. Certainly, there is a whole line of work bringing to bear all of these techniques in the application of embodied intelligence to warfare. Put aside all of that, uh, I think that the main thing I want to point you towards is there is a new breakthrough required to be able to continue to improve our ability to understand these systems, to be able to operate them over time, and to compose them and derive new bits of knowledge from them. That we really require that modularity property. We require abstraction. This is This is the work of our time, and this isn't just my opinion or Ziming Liu's opinion. This is you can look to people like Sutton, who is famous for things like the bitter lesson, who talks a lot about this within the context of the oak architecture. Abstraction is our goal at this point. There simply are no more books and magazine articles and emails to read that are going to give us meaningfully new knowledge beyond freshness of new concepts. The LLM approaches have taught us a lot. They've given us a lot of powers, but the next breakthrough has to be differently shaped. And so I want to bring in one more famous scientist who you may have heard of, and that, of course, is we had Brahe, who gathered all this data, and then we had Kepler, who turned it into laws which allowed us to understand the elliptical shape of the motion of celestial bodies. Eventually, we got to something substantially more general, and that, of course, is Sir Isaac Newton. And by the time we get to Newton, we really understand abstractly, deeply, fundamentally, compositionally, what is physics. We don't have that for artificial intelligence yet. There is a really shockingly small number of researchers pursuing that direction. I think it's an incredible opportunity and an exciting point in time to know that we are approaching that and that we seem to be accumulating the pieces that allow us to do the research to unlock the properties, which will ultimately allow someone to make those huge inductive leaps that allow us to develop a physics of AI, a general knowledge of how the theory of AI composes in such a way that really unlocks an entirely new era. If you can imagine pre-Newtonian attempts to do physics with everything that came after, it's really quite an amazing era to imagine yourself progressing towards. Now, that is not to say that any of us should presume that the only important work to do is to be the next Isaac Newton or Johannes Kepler or Tycho Brahe. There are many things that need to be done. Personally, I'm most excited by the work on substrates, on tools, on the ways in which we can enable those new things to happen. I think it's quite clear that there are these advances that fundamentally change how productive people can be exploring science in a particular direction. So for as much as I've bagged on dense MLPs, they've been my career for the past decade. I worked for a long time on PyTorch, and the advances of bringing GPU-accelerated deep learning techniques to everyone within all flavors of ML have been staggering. They have been literally world-changing in ways that I think are huge, important points within the evolution of technology that we should all celebrate for their advances, but also recognize they've left us with really quite the check to pay. Um, Due to the success of web scale data sets and large language models at the scale at which they currently exist, AI has become this paradigm which is dependent upon fantastic sums of capital that use huge amounts of energy and water and have a lot of second order consequences that people don't like, inclusive of all of those environmental impact things, all of those economic impact things. But where these models are useful, people are pretty concerned with things like sovereignty. When you look to the search for compressible knowledge, for understanding the structuralist approaches to AI, and the search for a physics of AI, I think you can see a different sort of science that sits beyond the one that we have today. And it goes through this path of making those insights that allow us to dramatically accelerate those superior techniques, which have different trade-offs, where we can work towards the goals of having more compressible, more socially compatible, more supervisable and interpretable methods. It's not going to be easy. I'm not going to make any predictions on timelines, but I think we're already at the beginning. We've been staring up at the stars for a long time. We've been reasoning about what it might mean to create things which have an intelligence like we have an intelligence, like life has an intelligence. I don't know if cans are they going to be the path towards that? I don't know. But what I do know is that the search for this type of intelligence, the building of tools that open up new methodologies that have these advantages of compressibility, of efficiency, of interpretability. This is the work that is really going to be some of the most important work. These are the revolutions that sit beyond the current LLM era. And if you, like me, are eager for a day in which people do things that are more advanced than current LLMs, that use models that they control, that are on infrastructure that is more sovereign to them, where scientists understand more mechanistically what their methods do, why they do them, and can make guarantees to the rest of society, well, then I think there's a ton of opportunities out there for you to go chasing. I know I will, and I hope you will as well. I've been Jeff. This has been Iterative Refinement. Be well.